Hello, can you hear me?
Yes, sir.
Okay, I apologize. There was some problem with Zoom. I kept trying to log in and somehow it wouldn't let me log in. Okay, so so we are going to be talking about a little bit about the project, the procedure to be followed, and then I also want to talk about there's just one little topic that that kind of got left out in the unit hydrograph concept. So maybe what I'll do is I'll spend maybe the first 10-15 minutes on this little topic from unit hydrographs, and then we'll go to the project, and then if we have time then we'll move on to the next topic. Okay, so let me share my screen 1 second. Okay, so are you able to see my screen? Is my screen visible?
Yes, sir.
Okay, all right.
Yes, sir.
So, so what we're going to talk about today is this concept of distribution graphs. Now, essentially, these distribution graphs are very similar to your unit hydrograph concept. Okay, the only difference is instead of giving you the amount of runoff at different time intervals, it gives you the percentage of runoff. Okay, so you can so you see how similar it is, right? So instead of knowing the amount of runoff generated by a unit rainfall excess rainfall event, it will tell you the percentage of runoff in successive time intervals. Okay, so all that means is it will tell you, so let us say a unit excess rainfall event produces 100 units of runoff. Okay, and that 100 units of runoff is produced over a time of, let us say, 10 hours. Okay, so in those 10 hours, how much of that 100 is produced in the first 1 hour, how much in the second 1 hour, the third 1 hour, and so on up to 10 hours, right? So it will tell you which time interval produces the maximum runoff, right? So for instance, let me just try to kind of illustrate this. So let us say I have a unit hydrograph that looks like this. Okay, so I have time on the x-axis and Q on the y-axis. So okay, so let us say this corresponds to some 100 units of runoff. If I simply convert it into in under every time interval, if I convert it into the percentage of runoff produced, okay, so that's what your distribution graph is. So are you able to see this this plot over here? You're able to see the plot? Yeah. So you see, this is what a typical distribution graph will look like. So instead of having on the y-axis, instead of having the actual volume of runoff, it is telling you the percentage of runoff, right, compared to the total that is produced over the entire duration of the unit hydrograph. Okay, it's fairly straightforward, right? There's nothing there's nothing sophisticated or complicated about this. It's just a different way of representing the same information. All right. Okay, so as you can readily imagine, if I know this kind of information, I can use it to do the same things that you would do if you knew the unit hydrograph, right? If you knew the unit hydrograph, you could calculate what the response to a given rainfall event would be. Similarly, if I know the distribution graph, I can use it to find out what the response to a given rainfall event would be, right? So the use of this distribution graph is precisely the same as what you would use a unit hydrograph for. Given a rainfall event, find out the runoff response. In just like you would use a unit hydrograph, you would use this distribution graph to do the same thing. Okay, any questions on this? Okay, so let us quickly solve a problem, and then hopefully that answers any questions that you may have about this idea. Okay, so let's read the problem statement. A catchment of 200 hectares area has rainfalls of 7.5 centimeters, 2 centimeters, and 5 centimeters. Should be on 3 consecutive days. Anyway, it says on 3 consecutive days. The average fee index can be assumed to be 2.5 centimeters per day. Okay, so far the information is very straightforward. You're given the total rainfall amounts on 3 consecutive days, and the fee index is also given to you. distribution graph percentages of the surface runoff which extended over 6 days for every rainfall of 1 day duration are 5, 15, 40, 25, 10 and 5%. Okay, so these are the percentages. So what this means is for every day of rainfall, you get 6 days of runoff. Okay, so that's what this, all of this terminology is simply trying to convey this information to you, which extended over 6 days for every rainfall of 1 day duration, right? So if I receive rainfall for 1 day, I get 6 days of runoff. And over those 6 days, the percentage of runoff are 5, 15, 40, 25, 10 and 5. Okay. So for 1 day of rainfall, you get 6 days of runoff. Those 6 days of runoff are given to you in terms of percentage. The first day produces 5% of runoff of the total. The second day produces 15%. Third day produces 40% and so on. Okay, so the percentages are given to you. The question now is determine the ordinates of the discharge hydrograph by neglecting the base flow. You're assuming that there's no base flow in this given, in this particular catchment, and you're trying to find out what the discharge hydrograph would be given the rainfall event 7.5, 2 and 5 centimeter on 3 consecutive days. All right. So let's go over the solution protocol or the procedure, right? So this is the information that's given to you. We go from time 0 or the first day to 9 days. Why do we go to 9 days? Why do we go to 9 days?
Lag by 3 days.
Yeah. So because every days of rainfall produces 6 days of runoff. So you have rainfall for 3 days. So you'll produce 9 days of runoff, right? That's how you can think of it. All right. So these are the rainfalls on the first 3 days. The rainfall amounts are given. Now, the next piece of information that was given to you was that infiltration loss is 2.5 centimeters per day. So over the course of a day, you will have 2.5 centimeters of infiltration loss. So you know the rainfall, the total rainfall, you know the infiltration loss through the phi index, and therefore you are able to compute the effective rainfall. 7.5 minus 2.5, that's 5. 2 minus 2.5 is less than 0, so therefore effective rainfall is 0. 5 minus 2.5, 2.5. Okay. Up to this point, everything is exactly the same as how you would solve your a typical problem if you're given the unit hydrograph, right? In this case, if you're given the unit hydrograph, what would you do after this? At this point, what would you do? Instead of giving you the unit hydrograph, in this problem, you are given the distribution graph. Let us say you were given the unit hydrograph. What would you do?
Multiply by the effective rainfall.
Multiply by the effective rainfall and lag by the appropriate times. Multiply by 5 for the first day, multiply by 0 and lag by 1 day. But since you're multiplying by 0, you don't have to do anything. Then the third thing, you'll multiply by 2.5 and lag by 2 days. Right? Right? So it's fairly straightforward. So that's exactly what we are going to do. Okay. So we have the distribution graph. So in this column, instead of having your unit hydrograph, you have the distribution graph. Right? 5% of the runoff happens on the first day, 15% on the second day, 40% on the third day, and so on. And of course, clearly you can understand that if I sum up all of this, you should get 100%, right? 5 plus 15, 20, 20, 20 plus 40, 60, 60 plus 25, 85, 85 plus 10, 95, 95 plus 5, 100, right? So all the runoff is accounted for. These are the distribution percentages over the 6 days, okay? So now what are we going to do? We are going to compute the distributed runoff for effective rainfall of 5 centimeter, effective rainfall of 0 centimeter, effective rainfall of 2.5 centimeters. What do we do? So 5 centimeters of effective rainfall will produce 5% of runoff on the first day, right? 5% of 5 centimeter is 0.25 centimeters, correct? 15% of 5 centimeter is, so this is what we are doing. 5% of 5% of 5 centimeter is 0.25 centimeters. 15% of 5 centimeter is 0.75, right? And so on. All right, you add all of this up, you will get 5 centimeter, correct? So this 5 centimeters of runoff is produced over 6 days in this format, and this is the distribution across the 6 days. right? The next column is easy. It's all zeros, no problem. The next column will be 5% of 2.5 will come over. Okay, so first of all, you have to lag it by, okay, so I'll fill in the numbers. So you've lagged it by 2 days. So the first day it will produce 0 runoff. The second day it will produce 0 runoff. The third day it will produce 5% of 2.5, right? 5% of 2.5 will come over here, correct? 5% of 2.5 centimeters will be the runoff on the third day, 0.125 centimeters, and so on. 15% of 2.5 will be here, 40% of 2.5 will be here, and so on. Is this absolutely fine? Any questions on this? Guys, please, if there's anything that requires clarity, please ask me now, because it's, you know, it's just a little bit different. So you just have to, you know, understand what exactly is going on. Is this absolutely clear? Okay. So now what are we looking for? So we found out what the distribution of runoff will be due to these 3 rainfall events over the 3 different days. What we are interested in is the overall runoff, correct? So the overall runoff will be simply the summation of these 3 columns. You just sum up these 3 columns, right? And so on, correct? But then this will give you the effective rainfall or the runoff in centimeters. You can always convert it back to what is that, volume or a rate, because you are also given the area of the watershed. Let me just go back. Oh, going back is a little bit. So the area of the watershed is given 200 hectares. Okay. So if you know the volume of runoff, sorry, if you know the runoff depth, right? How do you get volume of runoff? You multiply by area. If you know volume of runoff, how do you get the rate of runoff? Volume divided by your time. So in this case, it's the time step is 1 day. So you keep dividing it by, yeah. So let me, okay. So then here you'll have, so I've just converted it to cubic meters per second. Okay. Using, you know, using the area and the delta T, which is 1 day in this case. Okay. So 1 day I've converted it into, seconds, and therefore I've got the flow rates, the average flow rate for the duration of the the average runoff rates for every day over the duration of the total runoff generated, right? So it extends from day 1 to day 8. On day 9, runoff becomes 0. All right. Any questions? So this number, let me again, maybe we'll just work out one number. Yes.
Sir, 5 centimeters of effective rainfall occurred over 6 days, right? So
No. 5 centimeters of effective rainfall. Correct. 5 centimeters of effective rainfall occurred over 6 days. Yes.
And that is because of 7.5 centimeters of rainfall.
Correct.
So since it's happening over 6 days, will the second day rainfall have any effect on the ER value? 2 centimeters, will it not affect the ER?
Yeah. See, the thing is this: the 2 centimeters of rainfall that happens on the second day is not even enough to account for the infiltration losses, interception, all of those losses. We are just incorporating that into the fee index, right? So imagine this: I receive a major rainfall event, and runoff starts to happen. Okay, the runoff will take its own duration. It will take whatever 5 days, 6 days, whatever it may be. The next day, I receive a little bit of rainfall. Okay, if the rainfall amount is so small that it is not even able to that if you stand under a tree, all the trees are able to, you know, intercept that rainfall, that will not produce any runoff, right? Or if it just, you know, if it just fills the depression storage, that will not produce any impact on the runoff. Okay, so this is a, I understand what your question is, but the point is that the way we are looking at it, if you were to, you're looking at this phi index being a constant as a function of time. In reality, it may not be. Okay, in reality, your phi index may not be a constant. Phi index on the first day may be 2.5. On the second day, it may not be 2.5 centimeters per day. It may be 1.5 centimeters per day. Okay, because you're assumed that phi index is constant, right? So that's one of the limitations of this phi index approach, because the phi index, we just say, you know, it's the average thing, average infiltration losses that are encountered by an incoming storm. Okay, that average may not be representative of things as they are changing with time. So in fact, okay, so now that you have asked this question, I'll dig a little bit deeper. In reality, the infiltration loss may be higher on the first day. Okay, it may not be 2.5, because this idea of the phi index is based on an average. On the first day, if there's no previous antecedent rainfall, it may even be higher than 2.5. On the second day, it may be 2.5 or a little less than 2.5 and so on. And the third day, it may be even less than 2.5. But on average, it may be 2.5 centimeters per day. Is that okay? Okay, so let me just maybe compute one number so that it becomes very clear to everybody. So we'll take the first number, 0.25. So how do we compute this runoff? This runoff rate is obtained by 0.25 by 100 meters into 500 into 10 power 4 meter square. That's 500 hectares. So this will give you meter cube. Okay, so this is the runoff volume, but we are interested in runoff rate divided by what? How many seconds? You guys should memorize this. 86,400 seconds in a day. In one day, you have 86,400 seconds. Go back and you can check it out. Okay, 24 into 60 into 60 is 86,400. So if you do this, you will get this number, 5.8 into 10 power minus 2 cubic meters per second. Okay, so that's the average runoff rate over the entire day. All right, and similarly, the other numbers have been computed. You know, I leave it to you to check these numbers and ensure that everything's okay. All right. Okay, so now we are going to stop with that for the unit hydrograph. We are now officially done with it. So I'm going to stop sharing and I'll start sharing my QGIS. So I am assuming that all of you have received the data corresponding to the third project I had shared with all of you. Have you been able to download? Any issues? You should let me know right now. Okay, are you able to see my screen? My QGIS, is it visible?
Yeah, yes, sir.
Okay. Did anybody try downloading the data? Were you able to access the data downloaded?
Yes, we downloaded. I
Okay.
downloaded.
Okay, so it's, at least if one of you can download it, then everybody can download it. No issues. Okay. So now let me try to walk you through the process. Okay. So the first thing I'm going to do is I'm going to import the land use data. Okay. So for that, you have this this icon on the left hand side. This may be in different places depending on your the way you've customized your QGIS environment. You click on this. This allows you to import a raster layer. Okay. So I'll tell you what a raster is. So here I have this data has been uploaded on Google Drive and the link has been provided to you. These are the land use, land cover information for the individual districts. So you can pick any of the districts that you want. You're able to see the screen, right? The different districts. Are you able to see this window that's opened up?
Yes, sir.
All right. Okay. So let me just, for the sake of, we'll open Chittoor. Okay. So this is the land use, land cover data for Chittoor district. Oh, I think I did not. I forgot to upload the meaning for these different colors. Okay, I'll do that. But I'll just tell you what these different colors mean. Okay. All right. Okay. I don't think you're able to see my screen yet. So let me. Okay. Can you see my screen now? Showing the different, what these different colors mean?
Yes, sir.
Yes. Okay. So the, see, don't bother about remembering all these things, but what you need to understand is those different colors that you see in the LULC map correspond to these different types of land use. The dark red is your built up area, which means urban area. Okay. And these kind of shades of orange are the Kharif and the Rabi crop. And the Zaid is basically the summer crop. Okay. So these are the cropland. Double, triple crop has this, has its own color. Fallow, plantation, evergreen forest, deciduous forest, degraded forest, swamps, grasslands. See, okay, so you see all of these colors, but the area that you choose may not have all of these colors. Okay. For instance, in Chittoor, you may see this red, you may see this orange, this other orange, and then this maybe even this gray, this light green. You may see this other light green shade, and then this dark green and this other olive green kind of color, and then blue, which is water bodies. Okay. Of course, snow you will not see in Chittoor for sure. Okay. So let me go back to QGIS. So that's what these colors mean in QGIS. Okay. And if in case you want to find out what the different colors mean, you can use this eye symbol over here. You see this eye symbol, identify feature. You can click on it. If you click on it, it returns the value. So the value is 1. So if you remember, 1 was urban area, built up area. Okay. This other dark green color, I'm going to click on it now. It's 9. Okay. So if you remember, 9 refers to deciduous forest or evergreen forest or something like that. So that, okay. So this is the map of, this is the land use, land cover map of Chittoor. This red portion that you see over here, that is the city of Tirupati and the surrounding areas. Okay. So let me zoom in now to this area. Okay. So this I think is Kalahasti. This is probably Yerpedu. Our campus is somewhere over here. All right. So our campus is somewhere in this region, right over here. Okay. So now let us say you decide to, let us not put it right where our campus is, we'll put it in some other place. Let us assume that our campus was coming up, let us say somewhere else in Chittoor. Okay. Let us say it was coming up over here. I'll try to mark an area. Okay. So let us say our campus was coming up in this region. Are you able to see that shaded portion? Maybe not. Okay. I'll zoom in a little bit. Okay. Are you able to see this slightly shaded color?
Yes, sir.
Yeah, I'll draw it again. Okay, just in case. Okay. So now this shaded, it's unfortunate the color that is coming up, but anyway. Now you can see it much more clearly, right? So this is the area that I have drawn. So now this area, I've just drawn some kind of a simple polygon, and I'm getting 4 kilometers square. How many hectares is that? Any idea? How many hectares is 4 kilometers square?
400.
400, right? 4 kilometers square is 400 hectares, right? And what is the area of our campus? Oh, our campus is 200, sorry, what is that? 500 acres. Okay. Does anybody know the conversion from acres to, what is that? Hectares? 2.5 acres is about 1 hectare. Okay. So don't worry about it. Okay. These things you can very easily find out. So 500 acres would be about, how many hectares would that be divided by 2.5? 500 divided by 2.5 is 200.
200.
200 hectares. Okay, so this, whatever I've drawn here is 400 hectares. This is double the size of our campus, approximately. Okay, so let me just turn back the land use land cover map on. Okay, so let us say that this is the size of our campus. So within this campus, if you notice, now instead of just drawing a thing, I'm going to draw a polygon, a proper polygon, which will represent my campus. So for that, I will go over here, go to layer, and say I'll create a layer. Okay, do you see create layer? Create layer, new shapefile layer. All right. So I'm going to click on new shapefile. That opens up another menu. In this menu, I'm going to click polygon. So I'm going to create a polygon representing my campus area. Okay. So that's going to be, and then I'll say okay. So now it is going to ask me to, let me save it in project 3. Okay, I've already created it, but let me just create again, college campus 2.shape. So I'm going to create a college campus shape file. Okay. So now it has created an empty shape file. I want to describe the polygon that describes our, or I want to delineate the polygon that describes the campus area. Okay, so let me create that. So for that, I click on this pencil that you see over here on the top left-hand side. I click on that. So that allows me to edit this college campus shapefile that I've created. Okay, then you click on this tool over here, add feature. So you can add a feature. How do you do that? You click on that, and then you will see that my pointer, my cursor has become like a like a bullseye. Do you see this? That my cursor shape has changed, right? So then this allows me to click and create my polygon. So I'm going to left click at every vertex. 1, 2, 3, 4, 5, 6, 7, 8, and the last vertex you right click. Okay, then it will ask you what is the ID. I'm just going to enter some number 1. Okay. All right. So now I have created my college campus. This is the boundary of my college campus. Okay. So now you want to save this. You can just click save over here, save layer edits. So it has saved it. I'll stop editing. Okay. So this is my college campus boundary that I have created. So it's all very straightforward, nothing sophisticated. You just click, you create a polygon. In this case, I have made it a little bit bigger than our campus. Our campus is about 200 hectares. This one is 400 hectares, a little bit larger. Okay. So you can make this layer transparent and so on. There's lots of features available. I'll show you how to do that. So what I do is I click on this college campus shapefile, right click and select properties. Okay. I select properties, and then I go into general. No, sorry, not general. Style. Yeah, style. And then I click on this simple fill. Come over here and say outline. So instead of drawing a polygon which will have which will be filled with a color, I'm going to have a polygon that is just marked by its boundary. So I'll just put a nice bright red color and increase the thickness of the line. Okay. So now you see this red boundary that I've drawn, that is my college boundary. Now what you have to do is to find out what are all the different types of land use that exist inside my area, right? So inside this area, you can see there are about 3, 4 or 5 different colors, right? Let me just zoom in. So you see there is this orange, there's a slightly lighter orange, there's some green, there's a little bit of blue, and some dark green, and some slightly whatever, some other colors are there. Okay, so all of these different colors are there. You know the total area of your college campus, right? You can use this tool over here, measure area. You can click on that and it will give you the area of your campus. So let me again do that. It's about 400 hectares. I already know that, but let me again do it. You do it carefully so that you are able to. Yeah. So now when I've drawn it the next time, my error is up. So it's about 450 hectares. Okay. Anyway, doesn't matter. So your area is 450 hectares. Out of that, if you can see, the majority of the area is this whatever light green color that you see, right? Now let us find out what this light green color is. I'm going to click on this I button. Okay. And then click on this Chittoor land use map. I click on that. It says 5. So this light green color corresponds to land use type 5. And then this orange corresponds to land use type 2. And then this other orange corresponds to land use type 3 and so on. Okay. So now I will check what these different colors mean. 5 means double, triple crop. Okay. 5 means it's crop area. Basically, this entire portion is just crop area. Okay, 2 and 3 are Kharif and Rabi. Okay, so this orange over here is 2, that is Kharif crop. This other orange that you see is 3, which is Rabi. And then this green, the other green that you see in the background is number 5, which is double crop, which means it is cultivated both in Kharif and Rabi. Okay, so because I just randomly picked some area, it seems to be an agricultural area mostly. So can you not say that maybe around 70% of your area is just crop area? You can even verify it a little bit more accurately. I'll just try to do it. Let me draw another polygon now, which measures the area of this. Right, I'm going to draw something that looks like this. Okay, so I've shaded only this portion. That comes to about 350 hectares, 347 kilometers, sorry, 3.47 kilometers square, which is 347 hectares. So out of 450 hectares, 350 hectares approximately, don't worry about getting all, you don't need to be accurate to the single digit and so on. Okay, about 350 hectares is farmland. The remaining portion is some forest and whatever. Okay, so this other colors also you can find out similarly. Let me just do that. So this dark green color is number 9. Number 9, if I remember correctly, is deciduous forest. This other green is number 10, which is degraded forest. And then this other color is number 14, which is wasteland and so on. Okay, so you understand why I'm doing all this? Why am I finding out what the land use in this area is? Why am I doing all this? What is my objective in finding out what the
For finding C.
What is C?
Curve number.
Curve number.
The runoff coefficient.
Runoff coefficient. Okay, Cn is curve number, Aditya. Sorry, curve number is Cn. Okay, C is the runoff coefficient. All right. So now this is the part where it gets interesting. Now in this particular case where I randomly drew this polygon, it happens to be agricultural area. Okay, so let us assume that it is all going to get converted into a college campus. Obviously the farmers are not going to continue coming and cultivating inside the campus, so that cultivation will stop happening there. Okay, so but instead of having that cultivation, maybe some of it will get converted into built up area. Built up area means you'll have buildings and roads and other infrastructure and so on. So therefore that area is going to become impervious. Okay, the remaining area, instead of having farms, you may have some kind of gardens and stuff, parks inside the campus, to make sure that the campus is green and so on, right? Or you may have some forest which you already have anyway in this region. So what typically would be suggested is, when you develop the campus, you will try not to disturb the forest area, right? So this easternmost area, this portion of the area of the campus seems to be some kind of a forested land. You will try not to disturb that, and then there seems to be some kind of a river running through through this portion of the campus. That again you will not disturb. In this particular the area that I have chosen, most likely all of the construction activity will happen in this 350 hectares out of the 450 hectares, right? So in this region, the runoff coefficient is going to change. The rest of the area, the runoff coefficient will remain almost undisturbed. Okay, so now you can assume that out of this 350 hectares, maybe 30% or 40% will get converted to built up area, right? So therefore, appropriately, you will compute the runoff coefficient. For the remaining portion, you will assign some runoff coefficient typically expected of some kind of barren land or agricultural land that has been left vacant. Okay, so by this technique, you will estimate what the average runoff coefficient of the college campus is. Okay, so that gives you the C inside your equation Q equal to CIA, right? A, you know what it is. A is the area of your campus, no problem. Now comes the tricky part, which is the I, which is the rainfall intensity for which you have to design your the storm sewerage network or the side drains in your campus. You understand where we are going with this, right? So the objective is to find out the peak runoff rate that will be generated in this area. Okay, that gives you the that gives you the size of the drain required, right? So if your drain is able to handle the peak runoff rate, then it will definitely be able to handle the other whatever other runoff is generated, right? So your objective is to find out the peak runoff rate, for which you need the peak rainfall intensity. The peak rainfall intensity of your of this area needs to be known. Okay, so for that you already have the rainfall data for some one given year, 2018, right? That data has already been shared with you when you did the first project number 1. Okay, so using that, you will go into that database or into that data and try to find out which is the nearest rainfall gauge to this location that you have selected, right? So wherever you draw this polygon, you should know which area that is, so you can use Google Maps and find out where this area is, right? Because you always, anyway, you know the size of your you know your district, you know that your campus is coming up in this region, therefore you can find out which one is the nearest rainfall gauge to this college campus. You will assume that whatever is the rainfall received in that nearest gauge will be the same in your campus. Okay, that assumption you can make. Then you have to convert that daily rainfall data that has been provided to you. You will have to convert that into a rainfall intensity for a typical storm. Okay, for or not for a typical storm, for the highest storm that you are expected to receive, right? So what is the parameter that dictates finding out the rainfall intensity? Which parameter matters here? What do you think? So if I tell you that I need to find out the peak rainfall intensity, for which I have to design my drain network, which will carry the peak runoff, how would you go about finding out the peak rainfall intensity? Because you are only going to get, let us say, not let us say, you are going to get the daily rainfall received in the nearest rainfall gauge, right? So there may be, you look at all the daily rainfall values, you pick the day which received the highest rainfall. Okay, so let us say there was one given day in that year, 2018, which received, let's say 10 centimeters of rainfall. Now, if you divide it by 24 hours, you will get, some small rainfall amount, 0.5 centimeters per hour. Okay, so will you do that, or is there something else that you will do? You can assume that 10 centimeters of daily rainfall that was received on that given day, you can assume that rainfall happened over some duration. Which duration will you pick?
Time of concentration.
Time of concentration, right? So the time of concentration for your watershed, or for your, in this case, your watershed is your college campus, right? So how do you find the time of concentration for your college campus? You already have, we've given you one empirical equation, the Kirpich equation, which gives you the time of concentration in your uh, uh, in the watershed, given certain parameters. What are those parameters?
Slope,
What is that?
length,
Say that again, one by one.
slope of the catchment,
Slope of the catchment, then
Longest distance.
the longest distance that has to be covered. Okay, so let us try to understand how to find those out. Okay, so I'm going to zoom back into my college campus. So this is my college campus. So now in the background, I have the land use land cover. I will turn that off, and I'm going to now import the digital elevation model. Okay, so this data has also been provided to you. So I'll have to import the digital elevation model for Chittoor district. All right. So you see some kind of a black color in the background. So that is the digital elevation model, but I'll try to change the color such that it's a little bit more understandable. Okay, so instead of having, I'll have some colored map. Okay, so that gives you a little bit of a better idea of. Okay, let us look at the colors. Okay, so it shows only red in your area. So, but of course, if you look at the difference in the values, so red could be anything between 0 and 177.5 meters above mean sea level. So naturally, you'll have to curtail this. So let's make it 150. The maximum in the entire district is 710 meters above mean sea level, but we are only interested in the small area. So we will try to get a better idea of what the, okay. So now, see, I'm not going to try to explain every single detail of how to use QGIS. Some of it I want you to explore and find out. It's not very difficult. Okay. So it should really be doable for you guys. You guys are all, you know, so let me try to quickly get that done. Okay. So now these colors tell you how the elevation varies within your college campus. So now remember, I just picked this area randomly. I just drew it. I didn't know anything about this area. So let's try to find out which is the the darkest color that you see. Oh, sorry, the highest elevation that you see will be the lightest color here. Okay, because dark red means the lowest elevation, close to 0, and this blue over here is probably the highest elevation. Okay, so let us find out what the highest elevation is. I'll click on that location. It says 39. Okay, which means this point, there is a point inside my campus which is at an elevation of 39 meters above mean sea level. Okay, but now here's the thing, you will have to identify where is the flow happening on this campus. So for that, if you remember, I just go back to the land use. So there's some kind of a water body in this portion, in this portion of the campus. So looks like this is the area with what? Wherever there's a water body, that will, or if there's a river, that will be the highest or lowest point in the watershed. Lowest, right? So that might be the area. So let me go back to the so anyway, you can find out which is the lowest point in your watershed. So let's, maybe it's somewhere over here, I don't know. So it says 10 meters above mean sea level. Here I have another point which is 1 meter above mean sea level. Anyway, but looks like there's a river somewhere over here. So although you have lower points here, but there seems to be a river that is running somewhere around this region. So this region is about 19, 20, whatever. Over here I have 22, slightly higher elevations and so on. It's a mixed kind of region anyway. Okay, so you will try to find out what the slope inside your watershed is. Okay, find out, you can find the average slope. Okay, this particular region happens to be some kind of an up and down region. Okay, so it's not very clear if there's a kind of a slope in one direction. It may be sloping up and down in different parts of the watershed. So in that case, you are better off trying to find out what is the average slope that you expect in this kind of a region. Okay, so you can take the two extreme corners of the watershed and find out the elevation differences and find out what the slope would be, right? So that's one way of doing it. So now this portion, it's not very depending on the area that you pick, you may end up with, you know, different kinds of slope or different kinds of topography. So there's no one way of doing this. If you had to do it, you know, very precisely, or worried very about getting exactly accurate values of the slope, then you can do a little bit more laborious process. But maybe I would pick maybe 3 or 4 points and find the slopes and take the average slope, right? So maybe I'll do a point at the other one extreme. Here the elevation is 13 meters above mean sea level. At the other corner, I'm going to click, it says the elevation is 32 meters above mean sea level. So that's 32 minus 13, about 20 meters difference, elevation difference. You find out the distance between these 2 points. Let's find out the distance, measure line. So the distance between these two extremes is, it's about 2.7 kilometers. So you know the distance between the points, you know the elevation difference, you know the slope. Okay, so that's just one set of points. You can do a similar thing for the other two extremes. So here I have 13 meters above mean sea level. Here I have 36. So again, it's about 23, and then similarly, you calculate the length, you find the slope. You do this for, I've done it for 2 sets of points. You can do it for 5 sets of points if you want at different points in the watershed. You get the average slope. So you have the slope. The maximum length of travel, here again, if you had to do it very accurately, you would have to find out exactly what the path the water is going to take to try to reach the outlet of the watershed. Here again, I would just suggest that you take the maximum distance that you can. So in this case, I would say it's the maximum distance that in the entire watershed. Okay, that again you can do it multiple ways. You can this distance is one maximum, this is another maximum. You take the average of that. That could be a representative maximum length of travel inside the watershed. So that gives you your L, or the maximum travel distance, and your S, which is the slope. So now if you put it into your Kirpich equation, you know the slope, you know the length of travel, you find out the time of concentration. Once you have the time of concentration, let's say the time of concentration is 50 minutes. 50 minutes is about 1 hour, right? So you take your maximum daily rainfall divided by 24 hours. So that will, no, not divided by 24 hours, divided by 1 hour, I'm sorry. If you divide it by 1 hour, that assumes that all that rainfall that was received on that day, the maximum rainfall, happened in that 1 hour, which is an extreme case, okay? So if you do that, that will tell you what is the peak runoff. If you put that, so that will give you a rainfall intensity, peak rainfall intensity, right? If the 10 centimeters of rainfall happened in 1 hour, then your I, which is the I that goes into your equation, will be 10 centimeters per hour. You put that into the equation, you solve for it, you get the peak runoff rate, and then that is the answer that you're looking for, right? So it's really if you think about it, it's a simple, straightforward procedure, but you just have to go through these different steps. And depending on the area that you're looking at, you may get different types of land use. You'll have to estimate what the runoff coefficients for those will be. You will have to, depending on the topography, you will have to find out what the slope and the length of travel and so on will be for your chosen area. And from that, you will estimate what the maximum rainfall, peak rainfall intensity is, and the time of concentration, and thereby you will find out the peak runoff rate for your campus. Is that okay? I've tried to explain all the different aspects of this QGIS software here. Remember that there's tons of tutorials available on YouTube and so on. If you have any doubts about any aspect of how to use this QGIS thing, I'm sure a bunch of your friends might know how to use it. You can contact me if you want to know how to do some specific thing in QGIS, or there's YouTube videos available that teach you how to do different things with QGIS. All the data is available with you. I just want you to go into QGIS, import the data for your district, whichever your district you have chosen, and try to do this for your college campus, wherever you choose that area to be. And same thing, you will make a presentation, 4 or 5 slides maximum, right? Show the area, the district you have picked, the area of your campus, how large your campus is, right? What are the different land uses that you encountered there? What do those mean? And then you're done, right? So it's really a relatively simple exercise, but you will get an exposure to how to use QGIS, and then you can put that on your resume saying, I know how to use QGIS. This gives you an opportunity to learn QGIS. You can do so many things with it. Okay. Any questions? Okay. So shall we try to have this project done? So today's Thursday. Can this be done next Thursday? Can you guys present next Thursday? It's before Deepavali. I don't want you to be sitting on it during that weekend with your celebrations and all and working on your project. I know you want, but if you finish it off before the holidays or the festival, then you can chill and have fun. All right. So I'm going to assume that everybody's okay with next Thursday. It's not very difficult. All the data is there with you. It's a matter of just sitting, and maybe in an hour you can finish this project. It will only take an hour. Okay. Maximum, let's say 2 hours. Okay. It's relatively simple. All right.
Yes.
Okay. So so that's it for today. We are just bang on time. We'll meet again on Monday. All right. Take care, guys. I'll send you that LULC classes, what those different colors mean for the land use land cover. I'll upload that to the Google Classroom, so you will all have access to that. All right. Okay. So take care, guys, and see you on Monday. Bye.